Hello.
Hi, everyone. Nice to see you.
Good afternoon, Professor.
Hi. Okay. Let's see. Some people are still joining. Okay, guys. I think you got my email, which I sent you the day before yesterday, I guess. We still are in the process of trying to figure out the best way to approach these issues with long kappa and assign problems. So don't worry, we didn't forget about you, those who complain about some specific problems. Of course, we will try to take everything into account, but the issue is that it's not so easy with long kappa. It doesn't allow you much freedom in changes, and it's like from your side you are required to put right syntaxes and be very careful with answering questions. From our side, it's also not so flexible in terms of correcting some wrong problems if they happen. For sure, for most of you guys, you didn't get these problems because it's just maybe one or two problems from the pool and we randomize it for, but in the scope of all cohort of students, there are definitely quite many cases when it really requires attention. So if you feel that during the homework or midterm you get a wrong problem, please double check. Read carefully the problem, try to solve it, and if you still, after many times of double checking it, you are convinced that this is a wrong solution which long kappa provides, then make a screenshot of the answer which you submitted to long kappa's answer, and copy of detailed step-by-step solution of your problem. That submitted to me via email, and we will take this into account during the semester. So we will have some meetings with other professors who deliver this course for other sections, and we will take it into account. So far, it's also, this process is new for me, but so far, from 80 to 90% of complaints are not reasonable in terms of complaining for forgetting something in the answer or using comma instead of dot. That we cannot change. It's considered to be a mistake. But also people complain that the answer provided by long kappa is wrong and their solution is right. That's happened often, but eventually you figure out that it's not correct and it's actually in the contrary. But again, unfortunately, we still have these issues with long kappa, and we admit that they exist. So there is a chance that will be a problem with not correct solution, or a problem assigned like from topic which is really far away from our current stage in the course. So that could be also an issue. If it's just within 1 week, that is not so relevant because both homework and midterm exams, they are open source. No one limits you in access to literature or other resources. So definitely you can look it up. But if it's really far away from some topic which is not completely not related to currently covered material, that could be also a case to be considered. And we will work on this. So mostly now it's the main question how technically organize it that it will not mess up everything in Lone Kappa, and that is what we are working on. So yeah, if you have any questions regarding material, forces, work, kinetic energy, potential energy, you are welcome. As I remember, we finished our discussion last time, like mentioning about conservative and non-conservative forces. I believe today would be good to define what is what in more clear form, and go further with considering some cases of application of these concepts of kinetic potential and internal energy in terms of oh, excuse me, something happened with Zoom. Do you hear me?
Yes, yes.
Okay, yeah, but looked like that I was kicked out for a second or so. Okay, good. So let us first give a definition what is conservative force and how we define it. So for this purpose, there are main two definitions of conservative force. Imagine we have some system of coordinates, x, y, and have some 2 points on this system of coordinate, 1, 2. So first definition of conservative force is that the work done by conservative force will not depend on the trajectory, how we move our body from point 1 to point 2. And that means we can move it like this, straight, will be work done by moving directly from point 1 to point 2. It can be something like this. We are point A, let's say. And for conservative force, work done by moving body from point 1 to point 2 will be equal to work done by moving we are point 1, A to point 2. From 1, we are point A to point 2. And what actually matters is the initial and final position of the body. And these are defined by points 1, the coordinates of points 1 and point 2. So this is the one definition of conservative force, and another one is like this. If we come back, so let's say we move from 1 to 2 and then come back from 2 to 1 back. So if we come back to initial coordinates, work done by conservative force will be equal to 0. So second definition, it can be described as integral over closed cycle, like some closed trajectory when we move from point 1 and come back to point 2. Regardless the way how we do it, we can go in different trajectories, like have different passes, but the fact that it's closed, it comes back to its initial position. So the work over this closed cycle of some conservative force over will be equal to 0. So if these two conditions are satisfied, then the work is, the force is considered to be conservative. And of course, if one of these conditions are not satisfied, the force is not conservative. So let us consider maybe two examples of conservative and non-conservative forces before we move further and discuss the relationship between conservative forces and potential energy, which, like potential energy, we discussed last time. So let's again have a system of coordinates x, y. So with some unit vectors, so it's I, and here we have j. And let's say we have a body with initial, so it doesn't change the coordinate x, so x is constant, and it goes up. So I mean, it moves vertically from coordinate y1 to coordinate y2. So this is a direction of motion of this body. So let us, so definitely we have some mass of this body, and it has some weight, which is directed in opposite direction from the axis y. It goes down, please, mg. So let us consider the work which is done by gravity, which is, in this case, we consider the system Earth object, and Earth is represented by the gravitational field. So work done by gravity when this body moves from point described by position y1 to y2. So this will be work done by gravity equal to so in this case, we need to consider only projection of this force to the axis y, because projection of all forces and displacement to projection x is equal to 0. It's all aligned vertically. So it will be minus mg unit vector j multiply y2 minus y1, also vector, oops, sorry, not I, should be also vector J. Since both force and displacement are parallel to each other, we don't have any angle between them, so we can write that it will be equal to mg y1 minus y2. And because we have this minus, so we change y2 minus y1 to y1 minus y2. And if we come back, so this is first what we see from this equation. Work done by gravity depends only on position of initial point y1 and final point y2 on their coordinates. Anything from that is not relevant for this work, because if we move this body like this, so let's say we have some displacement in the direction of x, some negative and then positive because we go left and then come back to the initial x. The work done along in the direction along axis x will be equal to 0 because we don't have any projection of our force mg to axis x. So it will be equal to 0, and that's why work done by gravity will not change regardless how we move straight along axis y, or we do some curve around and come back to this and go to point y2. So this work is defined only by initial and final points for positions of locations of this body. And now assume that we move it back from y2 to y1. If in this case work done by gravity will be equal to mg y1 minus y1, because we consider first and initial and final position. And in this case, when we move up and down, come back to initial position, initial and final position are the same location. And this is equal to 0. So when we have a closed trajectory, work is done by the gravity force is equal to 0. So we satisfy two conditions for conservative force. And we can claim that the gravitational force is a conservative force because it's defined by potential of the gravitational field. And both conditions for the definition of conservative force are true. Okay. Let us go to another slide. And here we will consider a horizontal.
Excuse me, Professor.
Yes.
Can you show the previous slide?
Sure. Mm-hmm.
What does the last formula means? Why is it equal to 0?
Because here in the parentheses, we have y1 minus y1. We go, our initial point is y1, and our final position is described by coordinate y1. So we moved from one first position up and then moved from the up down to the initial position. That's
okay, thank you.
Yeah, that's why y1 minus y1 is equal to 0, and this product is also equal to 0.
Okay, thank you.
You are welcome. Yeah, let us consider a different case. Horizontal plane. And we have some body which is located on the plane. So let us hold first position with point A, and we move our body to final position, which is defined by point B on this plane. So let us do it along a straight line. So we have some friction between our body and our plane. So since it moves, let's say it moves with constant velocity, since it moves, we have kinetic friction, which is F kinetic equal to mu kinetic, the coefficient of kinetic friction, multiply N, which is a reaction of the plane, and when it's horizontal, it's equal to mu K mg. Okay, so we move it and we have some pass, let's call it S1. So it's length of our trajectory. Work done by a force, it's a constant force, so doesn't change with position. Work from moving directly from point A to point B will be equal to the product of our friction force, the kinetic friction force, and the path, the length of our trajectory, which is S1. Okay, now let us move it in a different way. So let's move it via point, let's call it C. So it will go like this. So work done in this case, a CV trajectory will be equal to constant kinetic friction force multiply S2. So the length of our trajectory. And we obviously see that the S2 is larger than S1 because we have longer trajectory in the second case. So in this case, since Fk, kinetic friction force, is the same for both cases, our work ACB is larger than work AB. So means that the first condition, definition of conservative force, is not satisfied, because if it's satisfied, this should not depend on trajectory and should be equal to each other, but it's not the case. So work done by the friction force depends on trajectory. So now let us check the second definition of conservative force. What if we, with another trajectory, come back to initial position? So in this case, let's say we have S3 here, it's some other curved trajectory. We come back from point B to A. In this case, work moving from A to A, like making some closed trajectory, will be equal to fixed constant kinetic friction force multiply the sum of S2 plus S3. And definitely this is not going to be equal to 0. That's why the condition for second condition for defining conservative force is not true. Work done by the friction force when you move body in some closed trajectory is not equal to 0. So friction force is non-conservative force. And this is what you need to remember in defining what is conservative and non-conservative forces. Okay, so now let us go further and consider the relationship between conservative forces and potential energy. So this is also kind of important concept to understand. So if work done within some system, like closed system, body, earth, or spring body, by internal conservative force, the change the work done by this internal conservative force is equal to the results in the reduction of the potential energy. So we can write that work internal conservative force is equal to X initial, X final, F X, where F is our conservative force, which depends on the coordinate X. Dx is equal to minus delta U. So we read it as work done by internal conservative force is reducing the potential energy of the system. So this can be rewrite in a, we can continue here, it will be potential energy in the final point minus potential energy in the initial point. And that's why when we want to find the potential energy in the final point, it's equal to potential energy in initial point minus here I forgot. So here should be minus because it's reduction of potential energy. So then it will be minus X initial, X final, our conservative force as a function of X dx. And this initial potential energy is really up to us how we define it, because it's just mostly what is convenient. If we have, for instance, some case where we have ground, so as a reference, and it's really convenient to set initial potential energy at the ground equal to 0, or it can be any other number. We just need to define it at the beginning and just stick to this, because eventually what really matters is change of the potential energy, not its absolute value, because its absolute value with respect to different origins can be different and defined in a different way. So now if we differentiate this, let's say d, like small changes in potential energy will be equal. So here we have some constant, it's either 0 or constant. When we differentiate, it will be 0. And then when we differentiate integral, we just get rid of the integral operator. So it's minus fx dx. And from here, we can write that f as a function, conservative force as a function of x, is equal to minus du dx. So it gives us definition of conservative force in terms of change of potential energy. So it is a differential form of writing this, our first equation. So this is integral form, and this is differential form. So force can be defined, conservative force can be defined as a negative derivative of the potential energy versus position x. And we can double check this. So for instance, on previous discussion, we were deriving potential energy of a spring. So potential energy of a spring is kx squared divided by 2. So it depends on the compression or extension of spring by this x in the second power. So according to this differential form of relationship between conservative force and change in the potential energy, let us try to define what will be the conservative force. For this purpose, conservative force as a function of x, actually this is spring force in this particular example, is equal to minus du over dx. And now we differentiate, take derivative of function u, which is k multiplied x squared divided by 2. And this is minus k2x divided by 2. So we cancel out this 2, and it's minus kx. And this is well known for you already, equation which describes spring force. So this is the relationship between internal conservative force with change in potential energy. And this is like mathematical, mathematical explanation. But if you think about it from physical point of view, it makes sense, because when we are talking about work of conservative forces, which for instance gravity, we don't care about external forces. We consider only work done by the conservative force inside the system. And it means if some body falls from height h on the ground, change in potential energy is mgh, and this is actually negative change, because potential energy in point 1 is larger than potential energy in point 2. So we reduced potential energy, And this reduction of potential energy happened because of work done by gravity. So work done by gravity caused negative change in potential energy. So that is the relationship between these two concepts. Okay, and maybe one more thing that we already, like here, everywhere consider just one-dimensional case, and it probably also good to highlight that it's true in all directions simultaneously. So in general, our conservative force, which could be a function of x, y, and z, it's not necessarily only function of one coordinate. It could be written in this form. So vector of our conservative force would be defined as partial derivative of potential energy over certain axis. Here it's I multiplied to unit vector in this, which defines the direction of axis x, then minus change in potential energy over coordinate y. I always mess them up. It's j, and then minus change in potential energy over z, and here we have k unit vector. So this is actually mathematically a definition of a gradient of scalar function, which is our potential energy as a function of coordinate x, y, and z. So in that case, if conservative energy inside the system depends on 3 coordinates, we should work with this equation and operate with partial derivatives, which are then projected, all these changes are along each axis of coordinate are projected on them. We are multiplying by these unity vectors. Okay, so maybe one example how it can be useful to apply this concept of relationship between potential energy, change in potential energy, and conservative force. So let us consider our lovely spring. Very good example. So we have some spring with attached body, and initially, well, no, it's actually only one case which we consider now. So it is in ground state. It's at, here we have our x, and it's located at x equal to 0. So here we can plot next to this spring with the body how potential energy depends on x. So here will be our potential energy as a function of x, and we know that it's square dependent. So potential energy for the spring is kx squared divided by 2. So it doesn't matter where we move, either x is positive or x is negative, we have square, so potential energy will always be positive. And it will be this kind of parabola dependence. Something like this, not very symmetric, but it should be symmetric. So now let us see what happens when we apply some force for some time, trying to move it, this body, towards left. So it moves a bit to negative x1. And at this point, we can see that the derivative of potential energy, du over dx, will be negative. It's less than unity. Why? Because this comes from the definition of derivative. Let's see if we have some function f from x. If this function goes like this, then derivative is a slope of this segment of the function. So we need to take delta x, delta f, and the derivative is a ratio in the limit of delta x going to 0 is delta f over delta x. If it goes up, delta f is positive and derivative is positive. If this function goes down, delta f is negative and derivative is negative, because we consider always last point minus initial point. So here we see the function u of potential energy as a function of position. It goes down from in the at negative values of x, and that's why derivative is smaller than 0, so it's negative. If derivative is negative, then our conservative internal force, which is spring force, is positive, because we remember that force is equal to minus conservative force is equal to minus du over dx. That's why our force is positive, spring force, and it is directed to the right along the axis x. What does it mean? It means if we applied shortly some force, moved it to minus x1, this creates a condition when the internal conservative force moves our body back to the initial position x equal to 0. If we apply initially some force which extends the spring, then we move this body to position plus x2. We see that here the derivative of this function du over dt is larger than 0, so it's positive. We see that this function increases with increase of x. If this function is positive, means that our conservative force, spring force, is negative, based again on this equation which we defined earlier. Means that in this case, this conservative force will push our body again back to initial position of coordinate, which is x equal to 0. So by analyzing the potential energy as a function of x, in particular its derivative, we can tell if the current position of the body is stable or not. So in this case, it is stable, because it doesn't matter in which direction we push our body, left or right, the resultant internal conservative force will be directed in an opposite direction and will force this body to come back to its original coordinate, x equal to 0. So it is resistant to some external disturbance, and the system, this position of the body is stable. So there could be another cases when position of the body is not stable. And then we see it from analyzing the functions of potential energy. Okay, maybe let us consider one of these examples. We still have a few minutes. Let's say we have some hill. And here is some ball, some body. So it will be also x. Here is x equal to 0. And here is our potential energy as a function of x. It will go similarly to this. Its shape will be as a function of curvature of this hill, but it doesn't matter. So the matter now is only the direction. So it will be something like this, because this is the height of position, and if we push this body to the left, for instance, for a short time, it starts to move to the left. We see here that this is our u over x. We see here at some minus x1, the derivative of our function is positive, of our potential energy. So it increases with increase of x. You see, from large negative, we go to small negative, and our function increases. That's why derivative of this function in this location will be larger than 0. It means that the conservative force, which will, like gravity force, which will act, some resultant gravity force which acts on this body in this position, will be negative. So gravitational force will be smaller than 0. And that is component of mg, like here, and here is the reaction of the ground. And here we will get some component which is, if it's alpha, so it will be mg sinus alpha. It's something similar to inclined plane. So this gravitational conservative force will be directed opposite to the axis x. It will be negative. And what it means, if we push it left, this gravitational force will even push it further. So this position is not stable. And in opposite to the previous case, which we considered with the spring, there is no force, conservative force, which will move our body to the initial coordinate x equal to 0. Instead, this conservative force will move our body even further. And the more we push our body from this position x equal to 0, the more it will be further driven by the conservative gravitational force. So for this position, for this system, we can claim that currently it stays in a metastable position, because we can get some equilibrium carefully condition when this ball will stay on the top of the hill. But with any minimum effort, it will just roll down, left or right, doesn't matter. And this is because of the shape of this function of potential energy versus coordinate x. So by applying this concept, we can easily define is our position stable or not stable. Okay, I think with this, we are pretty much done for today. And I guess on Friday, it's still time for, we will have time to consider some practical cases of application, the concepts of kinetic, potential energy, conservation of energy concepts, to see how it's more applicable on different examples. So you are more prepared for some problems in this talk.
Excuse me, Professor.
Yes.
Sorry for interruption.
No
So
problem.
in this particular example, there is no conservative force, or conservative force are temporary?
No, it is. Once it moves out from the initial position x equal to 0, so then we get this. So we consider conservative forces along axis x, because we have here potential energy as a function of x. So in the position at x equal to 0, there is no, in the direction of x, there is no conservative force. And once we move our body to the left or to the right, to some positive x, this conservative force appears. This is very similar to spring conservative force. If we come back to the previous slide, so here is also at x equals 0, there is no spring force. It's equal to 0 because displacement of the spring is equal to 0. It's in the normal condition. But once we move it left or right, we create this conservative force. So it's formed by the, realized by the spring, compressed or stretched, and its direction is defined by the function of, by the derivative of the potential energy function as of coordinate x. So in this case with spring, this conservative force which appears will push our body back to initial condition, initial coordinate. And in this case, because we have different profile of potential energy as a function of x, this conservative force will move it further from the initial coordinate x equal to 0, which means for first case, position, location of this body is stable. For the other one, it's not stable.
Okay, thank you.
You're welcome. Good, guys. Then have a good evening and see you on Friday.
You too, goodbye.
Bye-bye.
Thank you. Bye.